Good morning, guys. Today we're going to look at describing location in a distribution. That means we're going to describe where values are located in a distribution. So it's kind of like ranking them, figuring out where they're located relative to the other values in that distribution. So let's look at our setup for today. We have the win totals for all 30 Major League Baseball teams from 2012. Gone ahead and organized it in a stem plot for you. And started kind of doing a few calculations. So we know the frequencies. So these are kind of like our row totals. So I've done a split stem here, as you can tell. So we had one team that was in that 55 to 59 range, one team or two teams in that 60 to 64 range, four teams in that 65 to 69. So just kind of went through this stem plot, calculated the frequency of each row. So kind of like the starting part of building a histogram, so to speak. I then also calculated the relative frequencies on here for you. So 3% of the teams were in that 55 to 59, 7% were in that 60 to 64, 13%, and so on right there. Okay. We're going to come back to cumulative relative frequency here in a minute. Before that, I want to talk about kind of this location concept. So let's talk about the word percentile. Now, this is a word that maybe you're familiar with, maybe you're not. If you remember kind of going to the doctor, when you're younger, looking at test scores, your state test scores and things like that, ACT, things like that. You may have seen this word percentile thrown around. All right, so a percentile is nothing more than a way to rank individuals. That's all it is. It's just a ranking. Okay? It's not really saying how much better someone is. It's just stating the order in which people finish. Okay? So the idea behind percentile is we want to know what percent of individuals have a lower or smaller value. That's the concept behind what percentile means. So if you think back to like I said, when you go to the doctor when you're younger, if you were at the 65th percentile for height, that means 65% of other children your age had a smaller height than you did, a lower value in height. So you were, in that case, were taller than 65% of those other students. Okay? If you thought test score, so maybe you got your ACT score back and you were at the 93rd percentile in your science composite, or your science score. So that means that you had a higher score than 93% of the other students who took it at that time. So that's what percentile means. What percent of the individuals had a lower value? We don't know how much better you scored on the ACT on that portion. We don't know how much taller you are than those individuals. We just know the ranking of those individuals. So that's the idea behind percentile. So let's take these baseball teams from 2012 and let's calculate a couple of percentiles. All right, so let's say we want the percentile of the Twins. Now the Twins had 66 wins. So if we look at them, they are right here. So there's the Twins. So if we go by the definition of percentile, we can count how many teams have a smaller value. Okay, because percent just means part out of the whole, per 100, right? So it's part out of the whole. So our part with a lower value, smaller than 66 wins, was how many teams? Well, 3. We had 1, 2, 3 teams with fewer wins. And the whole was 30 total teams. So if we calculate that, that's 0.10 or 10th percentile. Okay. So that's how you calculate percentile. You just count how many had a smaller value, had fewer wins in this context, and then you get your, and then you just divide it by the total number that you had. All right. Take a second. I want you guys to calculate the percentile of the Nationals, who had 98 wins. I'll step to the side here. But look at the list, find the Nationals. I want you to calculate the percentile for the Nationals. And I'll wait right here. All right, hopefully you were able to get this answer here. Okay, so with the Nationals, you can see they're right here. It's the last team that had the highest win total. So we calculated up, there were 29 teams ahead of the Nationals, or sorry, below the Nationals, 29 teams who had fewer wins. And then we go and calculate 29 out of 30, and we get this 0.966 repeating. Now, to make that a percentile, this is where this kind of, it's iffy, kind of the context is going to decide. So you could think 97th percentile, because you could just think rounding, okay? But you could also have 96th percentile if we think true to the definition right there, okay? If you were kind of going to round to a whole number. The definition says what percent did you do better than? Well, we didn't do better than 97% of them. Or the Nationals didn't have more wins than 97% of them. They had more wins than approximately 97, but they did have more wins than at least 96% of them. So again, it gets kind of iffy on what you're looking at there as far as whether you're going to round up or round down on that. For what we're doing right here, I don't care which way you go, because I know if you're giving me that answer, then you're trying to think of it in true definition. But 97th percentile, because you know it's 96.6. That's very reasonable in this case. So I don't care which one of those, which way you go on that one right now. We'll look at situations where you have to go, you know, in one direction or another because of the context, but in this one, it's either way it works for me. All right. Now, the interesting thing is the Nationals were the best team in the league that year, right? Nobody had more wins than the Nationals. So I've got two questions right here that I want to kind of, you guys to take a few minutes and think about. We're actually going to talk about them in class tomorrow. But I just want to know what you guys think. So kind of write down your answer. We'll discuss it in class. Is it possible to have 100th percentile? And is it possible to have a 0 percentile? Okay, so pause it here for a second. See what you can come up with on those, and we will discuss those two things when you come to class. I'm going to set things up, and we're going to talk about kind of a way to graphically look at percentiles. So give me a second to get that done while you guys do this. All right. Hopefully you came up with good, well thought out answers. As I said, we'll look at those together tomorrow. I want to move to kind of a way to graphically look at percentiles. And that's something called a cumulative relative frequency graph, or an OJAP. That's a whole lot of words for what I like to think of as a percentile graph. Because in essence what you're going to get is we're going to be able to look at a point, look at a value, and try to estimate what percentage of the group, what percentage of the distribution actually had a smaller value in this case. Notice I'm saying smaller and not better or worse in the general terms. In certain contexts, it could be better or worse, but sometimes smaller is the better thing. If you're talking about cholesterol level, a smaller cholesterol might be a better thing. If you were talking about golf scores, a smaller golf score would be a better thing. If you were talking about points for a football team, a higher value would be a better thing. So I'm not always going to say better or worse. I'm going to try to keep in mind that, or keep the wording straight, that percentile means smaller value. So again, it doesn't necessarily mean is it better or worse. You've then got to look at the context to figure out is this a better or worse situation. But let's look at our Major League Baseball teams from 2012 and see if we can get a cumulative relative frequency graph or percentile graph going. So we're going to look at it in blocks of 5 right here. So if I thought of this like a histogram, so to speak. Okay, so remember we had over here the frequencies, and I broke them up by groups of 5 in that split stem situation. So I'm going to build a histogram off of that. Y'all can build that with me. And that's going to help us kind of figure out the cumulative relative frequency graph. So let's take a second. Let's turn this into a histogram. So if we looked at from a percentage standpoint, so for the 55 to 65, we were at 3 percentage points. Okay. From the next interval, we were at 7 percentage points. So what we can see here is the distribution of scores. That's all we have, distribution of scores. So with these distributions of scores, most of the teams had a high value. This is obviously skewed left. So there were a few, the fewer the wins, the fewer the teams that were over there. Now, the way a cumulative relative frequency graph says, I don't want to look at it as what's going on this block, this block, this block. I want to look what's going on at this block and everything that came before it. That's the cumulative part. So we've got our relative frequencies graph. Well, if we calculate our cumulative relative frequencies, that means let's look at everything in the interval, in all intervals before. What we can see is that this first interval that we had, there were no teams before it, right? This was the very first interval that we had, the 55 to 59 group. So before that, there was nothing that had come before it. So that's the cumulative relative frequency for that interval right there. Now, if we look at this interval right here, the 60 to 65 group, or 60 to 64 group, there was one team that came before it. So we know that one team out of all 30 teams is 3%. Now let's look for this next interval. So in this interval, the 65 to 69s, there were 3 teams that came before this interval. So before this interval, we had 3 out of 10, or 3 out of 30. So that gave us 10% of all the teams were before this interval. So that's the way you want to look at it. All right, let's look before this interval right here. So before the 70 to 74s, we had 1, 2, 3, 4, 5, 6, 7 teams. So when we had 7 out of the 30 teams, that gave us 23%. Well, hopefully you notice a pattern here, because what are we doing? We're cumulative. We're just adding all the stuff that came before. So what ends up happening is I'm just adding up what my relative frequencies beforehand were. So I had nothing plus the 0.3, and it gave me 0.3, right? And then I had 0.7 plus that 0.3, and it gave me 0.10. And then I had 0.13 plus the 0.10, and it gave me 0.23. So I can say, all right, now if I want the next interval, I need the 23% we have plus the 10% that was in that interval. So you're just adding up where you're at with what was in that prior interval. So we get 0.33, and we get 0.43, 0.60, or 0.53, 0.70, 0.90, and so now look where we're at. We're right here at this interval. So at this interval, we had 27 out of the 30 teams. So 27 out of 30 teams are coming forward. That's why we're at 0.90. Well, after this interval, so once we kind of left the data set, after this interval, we have all of the teams that we should have, right? So every team has occurred by the time we get to, say, the 100 to 104 group, okay? Remember, this is our 95 to 99. So if we kept going with our split stem here, when we get to that 100 to 104 group, we've had all of the teams present, and that's why you have to add that last 10%, that last group from that last interval. So you end up with 100% of the teams. Okay, that's how you get your cumulative relative frequencies. Now, I know that seems kind of weird, seems like a lot, but this is how the histograms kind of tie into it. All right, so let's look at the end point of each interval. So at the beginning of this interval, how many teams had 55 wins? Or think of it as percentile. How many teams are there? So how many teams had fewer than 55 wins? 0 of them. There were 0 teams with fewer than 55 wins. All right. By the time we get to the next interval, so by the time we get to 60, how many teams had fewer than 60 wins? Well, we just had that one team, so that was at that 3%. So you see how we went from 0 up to 3 as we came across that interval. So that's the same thing as the height of that bar right there. Okay. Now, by the time we get to our 65 wins, as we saw over there. By the time we got to 65 wins, we had 3 teams. Well, that was our 10%. Okay? So 10% is up here. Well, all that is taking this 7% and saying, okay, now I'm going to start here. This is my new floor. So I just shifted that 10% bar, or that 7% bar up. So here was my 3%. Then I took the 7% there and we shifted it up, and that puts me at the 10%. Okay. Now the next interval, the 65 to 70 group, that 65 to 70, that was 13%, right? That was a big old jump. So I'm at 10. Well, I'm now going to shift up 13%. So from 10 to 13 is going to put me at that 23%. So we're just taking our histogram, and where one ends, the next one starts. So then you're going to add a 10% bar, you're going to add another 10% bar, another 10% bar, a 17% bar, a 20% bar, and then a 90% bar. Or sorry, a final 10% bar to that 90%. So all we did was take the bars, and where one bar would stop, we would just shift to the next bar for that next histogram up. And then take the next one and shift it up to the next. So what we get are these points here to provide us with our cumulative relative frequency graph. So our cumulative relative frequency graph is just taking the histogram and looking at not what was in that interval, but what was in every interval before. Now again, if you have trouble seeing it with the histogram and with all this stuff, just go back to like we did before. Just count how many things before. How many were before 55? None. What percent was before 60? 3%. What percent was before 65? 10%. What percent was before 70? 23%. That's where all those points come from. So you're just counting what percent came before each of those values. So it kind of gives us a couple of different ways to look at the cumulative relative frequency graphs. Now, I just want to understand how it's built. You're not going to have to build them that often. We've got an activity we'll do later where I'm going to have you build one, and that's the last time you'll have to build one. You just need to understand kind of what it's telling us. So how is this a percentile graph? Well, because how do we calculate it? When I look at a value and I look at the height of the point at that value, I know the percentage of teams that had a smaller value than that, okay? Because that's how we calculate it. So let's go and answer a couple of questions. So let's look first. What is the median? All right, so I need to think of, anytime I'm dealing with cumulative relative frequency graphs or OJAGs, I need to think of it from a percentile question. So I need to think percentages. So what does median mean from a percentage standpoint? Well, median is the point with 50% is the midpoint, right? So 50% of the values are less than. So we would think of it as the 50th percentile. Thinking of it as the 50th percentile. So that is an easy question to answer. What is the 50th percentile based on this graph? So how do I get that? I go to my percentage. So here is 0.5. That's the median. I work straight across. Okay, right about there. And then we come down, and let's see if I can straighten that up a little bit. Yeah, that's probably about right. So if we looked at this, the median in this case, the 50% mark, when we go straight across to our curve, and then drop straight down to see the value that corresponds to the 50th percentile. That looks like it's probably about 81, maybe 82 wins, just depending on how accurately I sketch this. So we'd say approximately 81 wins is the 50th percentile, is the median. Now we could take all those numbers, throw them into the data set, and we can probably see what the median is. But based on this, we don't have to. We can just sketch it or eyeball it from this sketch. All right, so let's talk interquartile range. So I want you guys to take a second, think of interquartile range from a percentile standpoint. Those are a couple percentiles we've actually worked with before. And I want to see if you can tell me what the interquartile range for the number of wins was for the 2012 Major League Baseball team. So I'm going to hang right here for one moment while you work on that. All right, so hopefully you got an answer that looks like this. Okay, so as we can see, we remember interquartile range is just Q3 minus Q1. So how do we think of Q3 and Q1 from a percentage or percentile standpoint? Well, Q3 and Q1 represent the first quarter and the third quarter, so they're already a ranking. So Q3 would be like the 75th percentile. It has 3/4 of the data to the left of it, so with smaller values. And then Q1 is just the 25th percentile. It has 1/4 of the data to the left of it, so small with smaller values. So 75th percentile minus 25th percentile. So if we come over to the percentage axis, 75% is somewhere right around here. And if we work across and then drop down, it looks like it's around 90. 25% would be down here, between 20% and 30%. Work straight across to our line, and then drop straight down. It looks like we're somewhere around 73, 74. So I estimated at 73. So if we do 90 wins minus 73 wins, that puts us at an interquartile range of 17 wins. So based on this cumulative relative frequency graph, we can answer a lot of questions about how values or individuals are ranked, where they're located relative to other values or individuals, and we can estimate things that work off of percentile. So I could say, what's the percentile of 64 wins? And 64, go up to the curve, come across, and you can estimate if a team had 64 wins, where would it have ranked? How many teams would it have beat in this case? All right, two more things I want to talk about today. One is ZScore, or also known as standardized score. And then we're going to talk about transforming data, or making kind of uniform manipulations to data. We're going to jump on the calculator for that one, so make sure you have your calculator out when we go to this part here. But first, let's look at ZScore. ZScore, or standardized score, is really just a way to look at relative position. So it's something we use to compare. It tells us relative position. We use it for comparing. Tells us relative position. What does relative position mean? It means where is this value located within its group, and not how much did it beat things by and stuff like that. It's just where is it located, where is it ranked within the group, so we can use that to compare to other groups. So where this gets used a lot is if you're comparing two very, very different groups, but you still want to see how individuals rank within the groups. A common example we'll use is like ACT score versus SAT score. So if you know where you ranked on an ACT score, or sorry, how you did on your ACT and how you did on your SAT, and you're not really sure which one did I actually do better, because one's a score out of 36, the other one's a score out of 1600 or 2000, or however they're doing that one now. They're not numbers that you can actually compare side to side or side by side. So we need some way to look at them as a relative. So really, where did I rank in one versus where did I rank in the other? So that's what ZScore does. So it works off of those percentile ideas of ranking things, but it's not using percentiles. It's not just using straight percentages. It's going to look at our relative, or our position relative to the mean. Okay, so when we talk about tells us relative position, we're going to calculate that by looking at a value it's distance from the mean and dividing by its standard deviation. Okay? So you'll see this formula, z is equal to x minus x bar over standard deviation. So how far am I from the mean? So if it's positive, I was above average, I was above the mean. If this difference is negative, then I'm below average, so I'm less than the mean. And then let's make that relative to the standard deviation. How spread out was the data? So if I have something that's going to have probably a big spread, like SAT scores, compared to something that's going to have a very small spread, just because it has a smaller scale, like ACT scores, I don't have to know, okay, I was 200 points above average in this one, and I was only 2 points above average in this one. Well, that's not a big deal if the spread for one is 1 point and the other one's 100 points. Okay, both of them, you were 2 standard deviations above average. So that's what it's looking at. It's taking your distance, your position as it relates to the mean, and then scaling it based on what was the overall spread of that group, of that distribution. All right, so I've got 2 teams that we're going to look at here. So we're going to look at the 2012 Giants. They won the World Series in 2012. The league had 81 wins that year. The standard deviation for number of wins was 11.9, and the Giants had 94 wins. Okay? What we want to do is we're going to compare that to the 1954 Giants, who had 97 wins. So they had more wins, so we're going to figure out, okay, which team was actually better? Because these guys won the World Championship also. So was it the 94 win team or the 97 win team? Well, this team won more, but were they actually a better team compared to the rest of the league that year? So we're going to kind of calculate these 2 Z-scores and figure out which one was the better team. All right, so let's work this one together. So if I want the Z-score for the 2012 Giants, I need to get the the value from 2012, so they're 94 wins. So X stands for the individual, okay, individual value, minus the mean for that year, X bar. Now I know we should probably be using mu since it's a population, but that's just the symbol that we use. They're interchangeable at this point because our sample and our population means don't change, okay? So 81. So there were 81 wins for the league. There were 94 wins for the Giants that year. And then the standard deviation. So we have population information. That's why we're using sigma. So that's 11.9 wins. So we can look at the Giants from 2012 and we see that they were 13 wins better, right? So they had 13 wins above average. But the average team, remember standard deviation is typical average, or typical distance from the mean. The average team was either 11 or almost 12 wins above or below, right there. Okay, so they weren't much above average if we look at it. So if you'll throw that into the calculator, 13 divided by 11.9, you get 1.0, I think 1.09 is what that comes out to be. So their Z-score is 1.09. Okay? Wins. It doesn't have a unit. I was going to put wins there, but 13 wins divided by 11.9 wins on average is just 1.09. Units cancel out. So Z-score for 2012 is 1.09. They were 1.09 standard deviations above average. So slightly above average. Or sorry, slightly 1 whole standard deviation above average. Now let's look at the 1954 Giant. All right, so using that same formula of wins minus mean divided by standard deviation, I want you guys to calculate the Z-score for the 1954 New York Giants. And I'll wait right here for a second, let you get that calculated. All right, hopefully you're able to get this answer. So as we can see, when we do the value, 97 wins, minus our mean, 77 wins, and divide it by standard deviation, you get 20 divided by 18.5, which is 1.08. So based on these 2 Z-scores, I want you guys to take a moment and answer number 3. relative to the year that they played, which World Championship Giants team was better and why. So which one was better in the league that year? So I'm wanting to know kind of who was more dominant of those two teams, and then kind of justify that for me. So I'll give you a minute, just look at what we've done, see if you can come up with a conclusion. And hopefully it'll look like what I got when you get your answer. And I'll wait right here. All right, so as you can tell, I came to the conclusion, and hopefully you did too, the 2012 Giants were better because they had a higher Z-score. It was only slightly higher, 1/100th of a point, but it was a higher Z-score. So that means they were more standard deviations above the mean than the 1954 Giants. So it just means they were more above average. Let's kind of look at some reasons why that may be. They had fewer wins than the average team. And so it looks like the league was a lot better this year, because here the average number of wins was 77. Here the average number of wins was 81. So the league average was higher. Here there was a much smaller standard deviation, which is the big thing. There were a lot more bad teams this year. Okay, so that's what that's telling us. The scores were spread out. So not only was the mean a lot lower, the bad teams were a lot lower. So that means there were a lot more bad teams in the league that year. So that's why these guys were more impressive to get as many wins they did against a better league in a more competitive league. So that's kind of how we can look at what that's telling us. So when you're comparing two groups, we're just calculating the Z-scores, and higher Z-score wins to be the better in this context. If we were looking at something like we talked about before, where we're talking about 100-yard dash times, I wouldn't want to have the higher Z-score in that case, because I would want lower value. So in that case, the better person, the individual who performed better, would actually be the person with the lower Z-score, because we're wanting low values in that case. So winning and losing, performing better or worse, that's all relative to the context. But as far as ranking, Z-score is going to rate which one's above, which one's below, which one's to the left, which one's to the right. All right, so let's jump to the calculator real quick. I want to talk about transforming data. So on your sheet, you've got kind of the three data sets already together, but I'm going to throw them into the calculator. We're going to talk about that. Transforming data means making a uniform change to every element of a data set, either through addition, subtraction, or multiplication, division. Remember, division is just multiplying by a reciprocal. So what we're talking about is making the same change to every single value in the data point. For example, if I had a company and everybody got a $5,000 raise, then all their salaries would increase by $5,000. So that would be a transformation. Everybody gets the exact same change. All right, so let's just look and see at what our starting point is. All right, so we have a stem plot here of the win totals for the 30 Major League Baseball teams back in 2012. Let's figure out their measures of location and spread. All right, so if I go into stat edit and key in my all 30 teams, so we've got them keyed in there. We're going to stat calc and run one of our stats on list one, so second one. So when I do that, I can get all my goodies here. So let's look at the measures of location. Mean, that's X bar, is 81. Median is 82. And there are my quartiles, 72 and 93. All right, so we can see our measures of center, or measures of location, 81, 82, 793. We can see the shape is left skew based on this stem plot here. All right, let's get our measures of spread. So in the measures of spread, we could look at range, maximum minus minimum at 43. Quartile range is 21 because it's 93 minus 72. And standard deviation, that's sigma x, that's 11.7. So we can get our measures of spread also. All right, now let's look at a couple of transformations. So let's say that every team for some reason had to forfeit 30 wins. Well, when you forfeit, that means you lose those wins. So what we would do is take 30 off of every single team. It looks something like this. The 55 team becomes a 25 and so on. Now, if we're going to throw that in the calculator and see our new measures of location and spread, we just grab the calculator here. Now, when I go stat edit, I'm show you a little trick for transformations. Go up to L2 and just say, okay, I want to take my list 1 and subtract 30 from each value. So I did that up here in the header, list 1 minus 30, and it gives us that data set. Now we can run one of our stats on list 2. So when I do that, we see that our mean is now 51, median is now 52, and quartiles are now 63 and 42. So we can see that the data set, those measures of location, actually changed. And how much did they change by? Well, they all decreased by 30. Well, that should make sense because we just took 30 off every value, and these are values from the data set. All right, well, let's talk about the spread now. If we look at the graph, does it look like it's any more or less spread out? No, it looks the exact same as it did before. So let's look at our measures of spread. If I talk about my range, 68 to 25, well, it's still 43. If I talk about my interquartile range, 63 to 42, that's still a difference of 21. And my standard deviation is still 11.7. So we can see the graph, the spread did not change at all. And we saw that easily in the stem plot. Because all adding and subtracting does is shifts your graph left to right. It doesn't spread it out. So it just changes location, not spread. All right, well, let's say that we want to see the effect by multiplying or dividing. So let's say if for some reason I want to go to a point system and every team gets 2 points for a win. Well, if we take every team 2 points for a win, you'd get a distribution that looks something like that. Looks very much more spread out. It's still going to be a left skew distribution. That didn't change. It's just a more spread out left skew. All right, let's look at the numbers. So on the calculator, stat edit. Now let's go, we're going to go to L3, go up to the header, and let's say 2 times second 1, 2 times list 1. So let's double all the values in list 1. All right, now we've got all these same things we see here in our stem plot. So we're going to stat calc one of our stats, and I'm going to use it on list 3 this time. Let's see what happened to our measures of location. Our mean is now 162, so it changed from 81 to 162. Median is now 164, 182 to 164. Quartiles are 144 and 86. So what do we notice about those measures of location? Well, they appear to have doubled. Well, that makes sense because we just took all the numbers and multiplied them by 2. And since measures of location are actual numbers on the list for medians and quartiles, they should be doubled. They should be twice as much because we took them and physically multiplied them by 2. Well, let's look at our spread. We can see that it becomes much more spread out in the graph. Well, what happens to our measures of spread? Well, our range goes now 110 to 196. So that's 86 for the range. Interquartile range now looks like 42, and our standard deviation looks like 23.4. Well, that's pretty curious because 86 is 43 doubled. 42 is 21 doubled. 23.4 is 11.7 double. So just like the graph became physically more spread out, it's got twice as wide. The measures of spread also got twice as wide. So let's see if we can kind of create some general rules. Well, we noticed that the shape, no matter what we did to it, stayed the same. It was left skew every time. Well, we can see when we added and subtracted the measures of location, they changed by 30 when we subtracted 30. But the spread didn't change at all. It stayed the exact same spread because we just took the values and moved them back, all of them back 30. So everybody got moved the same distance, so they have the same spread. Multiplying and dividing, we can see that the mean actually doubled, median doubled. So all these values changed by that factor of 2, as did the spread. The graph visually got more spread out, twice as spread out. So that showed up in our measures of spread as well. All right, so we should always be able to see is that the shape will stay the same. Measures of location, they change no matter what happens because you're taking values and making changes to them. But your spread only changes if we are multiplying and dividing. So if we go back to that example with all those employees that make an average of $30,000 a year, I don't have to grab a calculator and type in everybody's data and then add $5,000 raise to everybody to then calculate an average. I should just be able to know that if everybody got a 5,000 raise, that average of 30,000 also increases by 5,000. So now it's a new average of 35,000. That's what we want to be able to accomplish with this idea of these rules and observations from transforming data. Okay, so that's it for kind of describing where things are located within a distribution, whether it be using percentiles or Z-scores, or how we can change some of those locations with transformations. So that's it, and I will see you guys in class tomorrow.